Okay, this video is going to cover all the gases involved in our combined gas law. You have the combined gas law that you see right there. It is on your formula chart. This is a combination of all the other gas laws that we're going to talk about in this video. This is really the only important one because everything else is combined into it. But this is going to go back. You're going to do a lot of cross multiplication division. So make sure you have a calculator handy. So let's get into it. The first thing you need to do when you're doing these calculations is track your variables. Your variables are right up here. P is pressure, V is volume, N is moles, T is temperature. We can write that if we want. You can fast forward through it if you don't want it. Okay, so the example calculation. What would be the volume in liters of an 8.9 liter sample? So our first volume, volume 1, is 8.9 liters of a gas at 100 degrees Celsius. So temperature 1 is 100 degrees Celsius. Remember, you must convert to Kelvin. So we're in Celsius, so add 273 to that, and we get 373 Kelvin. And 113 kilopascals. So pressure 1 equals 113 kilopascals. If conditions were changed to STP, remember what STP equals. Temperature 2 will equal 0 degrees Celsius, which is 273 degrees Kelvin. And we just add 273 to your Celsius. And pressure 2 will be 1 atmosphere, which we have to be equal to kPAs. Or everything has to be the same. All of our units has to be the same. So if you look at your conversions, 1 atmosphere equals 101.3 kilopascals. And we're trying to find the final volume. So some of you like to plug in your numbers first and then rearrange them algebraically. I'm more of a fan of maneuvering my letters before plugging in numbers. So you see we have pressure, volume, and temperature. We don't even have moles in this question. If it's not in the question, you can either put it as a 1. I just tend to ignore it completely and just act like it's not even there, which is fine. So now we have P1, V1 over T1 equals P2, V2 over T2. You're going to get a lot of practice with this, but remember it's a cross, multiply, and divide. We are trying to isolate the V2 right there. That's our goal, and we are going to get to our goal. I'm going to use a different color. It's black. So what we're going to do is we're going to cross multiply first. So we're going to multiply these two together. So it's P1, V1, T2 equals these multiplied together. This that we mean by cross multiply. So it's P2, V2, T1. So now we've got what I call a linear equation. And now if I want to now we're still trying to isolate this V2. So we're going to divide out everything else. So we're going to divide out P2 and T1. Divide out P2 and T1 by both sides. Remember, we're dividing it on both sides because it's multiplied in the original equation. Now our P2's cancel, our T1's cancel. So now we have P1, V1, T2 over P2, T1 equals V2. That's a lot of letters. Like I said, if you want to plug in your variables first, you can go right ahead and do that. So now we're going to plug in our values. So our first our P1, 113 kilopascals. We're going to use that. Always start with parentheses, 113 kilopascals. Times the first volume, which is what we started out with, 8.9 liters. Times the second temperature, which is what we're here, the STP. Make sure you're using the Kelvin value, 273. Close those parentheses. Divide. Parentheses again. Next, we're going to do the P2, which is right here. Remember to use the kPa value, not the 1 atmosphere. We have to do that because remember, our units have to be the same. Multiplying it by the first temperature, which was, make sure you're using your Kelvin value again, 373 Kelvin. Now, if you use your parentheses right, if you don't know, come check with me in class. I'll show you what to do. That will give you 7.26 liters. And there you go. So if you understand the cross multiply and divide, you can fast forward through the math part and check your math, make sure it's right. I'm going to show it every question for those who need the practice. So we're going to go ahead and move on. So this next one is Boyle's law. These graphs become very, very important. Remember the inverse versus direct. If we increase pressure and decrease volume, remember that's going to be an inverse relationship. They're opposites. Decrease pressure, decrease volume. So they're inverse. And here's P1 V1 times P2 V2. Remember, that's just the top of the combined gas law. So this is a portion of the combined gas law. It's only dealing with pressures and volumes. So real life application, when you breathe, your diaphragm moves downwards, increasing the volume of the lungs. When you increase the volume of the lungs, you decrease the pressure in your lungs, which causes the air from your mouth to rush inside your lungs so that you can breathe. So let's do a calculation. We have 1 liter of gas. So V1 equals 1 liter at standard temperature and pressure. So standard temperature equals 273 Kelvin, and standard pressure is 1 atmosphere. And it says it is compressed to 473 milliliters. So V2 equals, remember we got to convert this to liters, so move that decimal 3 places to the left, 0.473 liters. What is this new pressure of the gas? So P2 is what we're looking for. Now, it gave us standard temperature. We don't really need it, but we can assume that it's going to stay the same. So if temperature is not changing, we can just ignore it, and plus we know we're dealing with Boyle's law right here, P1, V1. So that's all we're really going to be concerned with. Okay, so now we plug it in. P1, V1 equals P2, V2. We're looking for P2. So we're trying to isolate this guy. Let's multiply that on the right, so we're going to divide out the other part. Divide each side by V2. There. You get P1, V1 over V2 equals P2. Now you can plug and chug your equation. P1 was standard, so it's 1 atmosphere, 1, times V1, which was 1 liter, so this is going to be really easy. Put that in parentheses, I guess. Divide it by volume 2, which was 0.473 liters. So 1 divided by 0.473 gives you 2.11, and that unit will be in atmospheres. There you go. Okay, moving on. Charles's law. This one is, once again, V1 over T1 equals V2 over T2. This is still just a portion of the combined gas law. It's just going to give you volumes and temperatures, and you can just ignore the rest. So now we've increased temperature, increased volume. So if they're both going up at the same time, these are direct relationships. So we can see that with our graph here. Straight lines tell us it's a direct relationship. So real life application. Bread dough rises because yeast produces carbon dioxide. When you put it in the oven is hotter than where you were mixing the dough, which causes the gases to expand, in other words, increase in volume, and the bread rises further. So let's do a calculation. Man heats a balloon in the oven. If the balloon initially has a volume of 0.4 liters, so our V1 equals 0.4 liters, and a temperature of 20 degrees Celsius. Remember, we've got to convert 20 degrees Celsius to Kelvin by adding 273. It's going to be 293 Kelvin. What will the volume of the balloon be? So we're looking for V2. I don't know why I called this T2. It should be T1. My fault. After he heats the balloon to a temperature of 250 degrees Celsius. So T2, it looks like a big number, but you got to pay attention to that degrees Celsius because you're still going to add 273 to convert it into Kelvin, which would be 523 Kelvin. Okay, so we have V1 over T1 equals V2 over T2. Remember that cross multiply thing we did earlier? Here we're going to do it again. We're trying to find the V2, so our whole goal is to get that guy by himself. So cross multiply V1 times T2 equals T1 V2. So we're still trying to isolate the V. Now that we've got our straight linear equation, we divide out the other guy. Divide T1 on both sides. Those cancel. But we end up with V1 T2 over T1 equals V2. Now we can plug and chug. Our first volume was 0.4 times our second temperature, which was 523. Remember to be using that Kelvin. Parentheses around the top. divided by our initial temperature, which is 293. If you used parentheses right, your calculations are correct. You should get 0.71 liters. Make sure you put that unit in there because it definitely does count. Let's move on to the next guy. Gay-Lussac's law. This one's talking about pressure and temperature. We increase temperature, we increase pressure. We see we have a straight line here, so these are going to be a direct relationship. It's a real life application. Air pressure inside the tire increases on a hot summer day. Great. Right now, it's November, so it's super cold. I just had to put air in my tires because my tire pressure went way down. And we can actually do this. I don't know why it's not the example problem. But we'll do some of these in class where we actually deal with real life stuff because this one's kind of fun. But the pressure on a gas energy container changes from 800 millimeters of mercury. So pressure 1 equals 800 millimeters of mercury to 215 atmospheres, or 2.15 atmospheres. So P2 equals 2.15 atmospheres. So remember, we're going to have to keep them in the same units. We start millimeters of mercury. I'm going to end in millimeters of mercury. You can convert it to atmospheres if you want. Not a big deal. So we start with 2.15 atmospheres, and 1 atmosphere equals 760 millimeters of mercury, which gives us 1,634 millimeters of mercury. And that is our pressure 2. And the temperature is found to be 40 degrees Celsius. So T1, once again, we got that degrees Celsius. We're going to convert that to Kelvin by adding 273. That will give us 313 Kelvin. And we're trying to find the final temperature. The final temperature would be T2. That's what we're looking for. So now let's play with the equation. P1 over T1 equals P2 over T2. Cross multiply. You get P1 times T2 equals P2 times T1. We're trying to solve for T2, so that guy's got to stay by himself. Divide the other one out. So divide the P1 out. It cancels there. And you get T2 equals P2, T1, P1. Now you just plug everything in. 1,634 is our second pressure, times our initial temperature, which was 313 Kelvin, parentheses, divide by original pressure of 800 millimeters of mercury. If you do the math right on all the calculations, it should give you 639 kelvins. Now, if you originally converted your P1 to atmospheres, you should get the exact same answer. If you don't, let me know. We'll figure out where your calculation went wrong. It's the next old dead guy. This guy gets the award for the most obvious law. If you increase the number of moles, the volume increases. Well, no joke. If you put more into something, more is there. But you see, once again, your direct relationship. So moles and volume are direct. So V1 over N1 equals V2 over N2. Once again, still part of the combined gas law. So adding air to a balloon, which means blowing more air into the balloon, will increase the size of the balloon. Once again, duh. So the example, 36.2 moles of carbon. So N1 equals 36.2 moles. Occupies a volume of 5.2 liters, so V1 equals 5.2 liters. If 15.4 more liters are added, so V2, we started with 5.2, we added 15.4 liters. That one you have to pay real close attention to the words. Our V2 is 20.6 liters. Okay. How many moles of gas do you have? So we're looking for N2. That's our X. So once again, let's play with the equation. V1 cross multiply, V1 N2 equals V2 N1. And we are trying to find the N2, so this guy needs to stay by himself. Divide out the V1. It cancels on the left. So final equation is N2 equals V2 N1 over V1. Okay, so now we just plug and chug again. Our V2 was a 20.6. I'm going to do this down here. Times our original amount of moles, which is 36.2. Put that into parentheses. Sorry about the guy, it's kind of annoying. And then divided by original volume, which is 5.2. If you did your calculation right, you should get 143 moles. There you go.